Hi, welcome to my lab report 3 on estimating the mass of a black hole. So we have been given that the mass of the star which is orbiting a black hole is 1.989 into 10 power 27 kg, and we are given its xy coordinates as it orbits around the black hole with a time interval of 1 day, that is 86,400 seconds. So this data we were provided in a CSV file. So we are supposed to write a simulation program in VIDLE which will extract this data and then analyze it to calculate the net force acting on our star due to the gravitational force exerted by the black hole. So once we find the net force, we are supposed to equate it to the gravitational force exerted by the black hole on the star and solve for the unknown mass of the black hole. So that's what I have done. So let me show you my program. Let me first run it. So here you can see the black dot is the black hole, the red dot is the origin. So the black hole is not exactly at the origin of the reference frame as given in the problem, and the black arrow is the net force acting on the star due to the black hole, the net gravitational force. As you can see, it passes along the line joining the black hole to the star, and the red vector is the perpendicular component of the net force perpendicular to its instantaneous velocity, and the blue arrow is the parallel component of the net force. It's parallel to its instantaneous velocity, and you can see the vector sum is correctly shown here. The blue vector plus the red vector adds up to give you the black vector. So the simulation is working fine. Now we are supposed to calculate the mass of the black hole. So at the final instant of time, you can see that the program generated the output that the mass of the black hole is 2.38 into 10 power 31 kg, and the magnitude of the net force acting on it was 3.0 into 10 power 24 newtons. Everything is in SI units in this program. Now let's look at the data generated by the program in the form of a CSV file. So I've already copy pasted it in a spreadsheet. So I generated its position coordinates at each instant of time. So it generated a total of 1095 values. The index number which I used to step through the data points is shown here. These are the time intervals, and using the x and y coordinates I calculated the instantaneous velocity components along x and y. It's basically the final position minus the initial position divided by final time minus the initial time. So that gives the x component of velocity. Similarly, when I do with the y coordinates, I get the y component of velocity. So this first value of x velocity is obtained from x1 minus x0 by delta t, and the first value of y value is obtained as y1 minus y0 by delta t. So this is repeatedly done to get the final values. So you will find that the velocity values will be 1 less than the number of position values. So you can see here in my program I do it till 1092, the index. So index number is going from 0 to 1092, and the net force value is also calculated here, the parallel, perpendicular, and the mass of the black hole. So this is the mean mass of the black hole, which is 2.39 into 10 power 31 kg. Okay, now let me explain the code. So here I am initializing the star, which will appear as a yellow sphere in my simulation, and I scaled up its radius to 2 into 10 power 10 so that it will be visible on the screen, because the distances are of the order of 10 power 12. So x and y are of the order of 10 power 12 and 10 power 11 meters. So if you found the maximum x coordinate is 10 power 11 and the minimum x coordinate is minus 1 into 10 power 12. So the difference between the maximum and minimum is 1.3 into 10 power 12. So I want the diameter of the star to be comparable to this, so that's why I set it to 10 power 10. So then it becomes visible on my screen. Then the path of the star is shown in green color using this trail, and the origin is at 0, 0, 0. It is shown as a red dot, which is slightly smaller, so that's why I made it 0.8 e power 10 compared to 2 into e power 10 for the star diameter, star's radius. And the black hole I wanted to be bigger than the origin and in black, so I have made it color dot black, and its origin and its initial position is as given in the problem statement, which is minus 2 into 10 power 10 and 1 into 10 power 10 for the x and y coordinates. Then these three arrows I will use to show the net force, the perpendicular component of net force and the parallel component of the net force in the three different colors of black, red and blue. Then mass of the star also I have initialized as given in the problem statement, and universal gravitational constant is initialized here, and the time interval is initialized here as given in the problem statement. So my simulation starts at t equal to 0, and in this line I read the xy coordinates from the star data.csv file provided in the problem, and the initial position of the star is set here. Here the index value is 0, so it reads the first row of the spreadsheet of the CSV file and stores those coordinates as the coordinate of the position of the star at t equal to 0. Next, I find the x and y components of velocities. For that I created the list to store the x and y component velocity values. So the list will have the number of rows which is 1 less than the number of rows of the position values. So len of x gives me the number of rows in the position list. So less by 1 will be the number of rows in the velocity list. So when I multiply this number with the 0, what I get is I get 1094 rows having 0 stored in them. So the initial values in this list is all 0. Later I will populate it with the actual velocity values. So here I have opened this velocity data file to store the output values from my program. Okay, so in the first loop where I will calculate the velocities, I have to make the loop run till the last row, which is the 1094th row. So I set the index to vary from it's already initialized to 0, so it will go all the way till 1094. Yeah. So first I find the displacement in x. So x final minus x initial. So right now here this would be x of 1 minus x of 0, and x velocity would be this delta x divided by time. So this is stored in x0 here. Xvel of 0 it is stored. Similarly yvel of 0 will store the velocity calculated from y1 minus y0 by delta t. So I write all these values in the CSV file. Then I increment the index and the time, and when this loop is completed, my velocity list will have all the x and y components of the velocity from initial to final time. Next I am creating a new file to store the net force and mass of the black hole values. So you can see here up to mass of black hole I am going to store. So for executing this new loop, again I initialize my time counter, time to 0, and then I am incrementing it by delta t so that it will be matching with the index value of 1. So while finding the net force, I want my index to start with 1, so that my initial velocity would be whatever is the value stored in the zeroth row, and the final velocity would be whatever is the value stored in the first row. So here right now index is 1, so this would be xvel of 1 and this would be xvel of 0, so that when I find the delta v, it will be the velocity stored in 1 minus velocity stored in 0. Similarly, delta p would be final momentum calculated for using the velocity in 1 minus momentum calculated using the velocity in 0. So that's how I find delta v, delta p. Then this is dp dt. Using a program, it's very easy to do. Just divide delta p by delta t. So delta p is a vector, so dp dt is also a vector. And by Newton's second law, dp dt, rate of change of momentum, is the net force acting on the object. So we get net force directly here. And so now let's discuss the physics aspect. So as you can see here, the net by Newton's second law, net force is dp by dt, and p is a vector which can be written as magnitude of vector times the unit vector along momentum. If I differentiate it, then magnitude of momentum times derivative of unit vector plus unit vector times derivative of magnitude of momentum. So this term gives us the parallel component of net force, while this term gives us the perpendicular component of net force. So in the program we can easily calculate the unit vector of momentum and derivative of magnitude of momentum. So this term is known. Similarly, the net force, we just saw how we calculated easily from the position data provided to us. So we are just left with finding the perpendicular component of net force. So we will do it by algebra. Perpendicular component of the rate of change of momentum is total change in momentum, total rate of change of momentum minus the parallel component of rate of change of momentum. So you get dp by dt minus this term. So since we know these two, we can easily find this. So that's what I'm going to do in my program, as you can see here. So my unit vector along momentum direction, that is p hat, is obtained using this norm function from the initial momentum vector. So p underscore init dot norm, and the derivative of the magnitude of momentum is obtained by dividing the change in magnitude of momentum with the delta t, the time interval. So I used p underscore final dot max, so this will give the magnitude of p underscore final. And so the parallel component is this derivative of magnitude of momentum multiplied by the unit vector of momentum. So that's what I have done here. So this is going to be equated to the parallel component of net force here. Now the perpendicular component of net force would be the total rate of change of momentum minus the parallel component of momentum. So I equate the net force perpendicular component to this. And now let's discuss the physics behind finding the mass of the black hole. So as you can see in this graph, this is the xy coordinates of the position of the star which is orbiting around the black hole. So as you can see, the black hole position shown by this dot is not actually at the origin, it is displaced from the origin. And the gravitational force exerted by the black hole on the star is always along the line joining the black hole and the star, and it is directed towards the black hole as shown by this black arrow, and that is also the net force acting on the star. And the position vector of the star relative to the black hole is this red arrow and denoted by this r vector. It is actually position of star minus position of black hole. So this is what we will code in the program. So as you can see here, r is the relative position of star with respect to black hole. It is star dot pos minus black hole dot pos. And so by Newton's law of gravitation, we get that the gravitational force exerted by the black hole on the star is minus universal gravitational constant g multiplied with mass of sun multiplied with mass of the black hole divided by magnitude of the relative position of the star with respect to the black hole squared, and in the direction of the unit vector of this relative position vector. So we already know that the gravitational force is the net force, which we calculated from the program. We know the universal gravitational constant is 6.67 into 10 power minus 11. Mass of sun is given in the problem. Unit vector also we can get from the program, and magnitude of the relative position vector also we can get from the program. So now by doing the algebra we can find the mass of the black hole. So the algebra is done like this. This is a vector equation. Take the scalar form of it, you get this. Rearrange the terms and you get this. So now this is what we will code in the program. So net force dot mag into r dot mag2 by g into star dot m. So I'll show you where I did that. So you can see here net force dot mag dot net force dot mag into r dot mag2 by g into star dot m. So in each step it will calculate the mass of the black hole. So when we run the program over all 1095 steps, we should get more or less the same value of the mass of the black hole, assuming that mass of the black hole does not change. And that is what we got. As you can see here, it's 2.39 into 10 power 31. It's more or less same thing. 2.38 into 10 power 31, 2.39 into 10 power 31. It's pretty constant. 2.37, 2.36, 2.40, 2.41. So it's pretty constant. So for such a large number, obviously there will be some variation. So the maximum value of the mass was 2.41 into 10 power 31, and the minimum was 2.36 into 10 power 31. So the mean mass is 2.39 into 10 power 31 kgs. So I think that completes my project. Let me now answer the what if questions. So yeah, what does it mean? Question is, how are these three different from these three? Well, these three are the cause of the motion of the star. So there is a net force acting on the star due to the black hole, due to the gravitational force exerted by the black hole. That is what causes it to move and have a change in its momentum. So these changes in momentum, rate of change of momentum, we can easily calculate by observing the motion, by motion analysis using the tracker data. So this is representing the effects. So from this we can estimate what must have been the net force acting on it. So we can't comment about what is causing the net force. We can only find out the magnitude of the net force. So that's what it means. Now for the what if question, is it possible for me to find a value for the mass of the new black hole which is different from the mass which I already found for the original one? This is under the condition that the motion of the observed star remains unchanged and is affected only by the gravitational force of the new black hole. So will there be any difference? The answer is there can't be any difference, because our entire analysis is based on the motion of the star, and if the motion of the star is unchanged, then whatever we calculate from that would be the same every time we do the calculation. So again my calculation for the mass of the black hole would give the same result. And since we are told that the position of the black hole is also not changed, my formula which is used to calculate the mass of the black hole will be completely unchanged. So my final result would again be the same. So it is actually impossible to have the same position, motion for the star if the mass of the black hole is changed and only gravitational force is acting on it. Okay, so that completes my report.